Differential geometry of surfaces. In mathematics, the differential geometry of surfaces deals with the differential geometry of smooth surfaces with various additional structures, most often a Riemannian metric. Surfaces have been extensively studied from various perspectives, extrinsically, relating to their embedding in Euclidean space, and intrinsically, reflecting their properties determined solely by the distance within the surface as measured along curves on the surface. One of the fundamental concepts investigated is the Gaussian curvature, first studied in depth by Carl Friedrich Gauss, who showed that curvature was an intrinsic property of a surface, independent of its isometric embedding in Euclidean space. Surfaces naturally arise as graphs of functions of a pair of variables, and sometimes appear in parametric form or as loci associated to space curves. An important role in their study has been played by Lie groups in the spirit of the Erlangen program, namely the symmetry groups of the Euclidean plane, the sphere, and the hyperbolic plane. These Lie groups can be used to describe surfaces of constant Gaussian curvature. They also provide an essential ingredient in the modern approach to intrinsic differential geometry through connections. On the other hand, extrinsic properties relying on an embedding of a surface in Euclidean space have also been extensively studied. This is well illustrated by the nonlinear Euler-Lagrange equations in the calculus of variations. Although Euler developed the one-variable equations to understand geodesics, defined independently of an embedding, one of Lagrange's main applications of the two-variable equations was to minimal surfaces, a concept that can only be defined in terms of an embedding. History. The volumes of certain quadric surfaces of revolution were calculated by Archimedes. The development of calculus in the 17th century provided a more systematic way of computing them. Curvature of general surfaces was first studied by Euler. In 1760 he proved a formula for the curvature of a plane section of a surface, and in 1771 he considered surfaces represented in a parametric form. Monge laid down the foundations of their theory in his classical memoir L'application de l'analyse à la géométrie, which appeared in 1795. The defining contribution to the theory of surfaces was made by Gauss in two remarkable papers written in 1825 and 1827. This marked a new departure from tradition because for the first time Gauss considered the intrinsic geometry of a surface, the properties which are determined only by the geodesic distances between points on the surface independently of the particular way in which the surface is located in the ambient Euclidean space. The crowning result, the theorem egregium of Gauss, established that the Gaussian curvature is an intrinsic invariant, i.e. invariant under local isometries. This point of view was extended to higher dimensional spaces by Riemann and led to what is known today as Riemannian geometry. The 19th century was the golden age for the theory of surfaces from both the topological and the differential geometric point of view, with most leading geometers devoting themselves to their study. Darboux collected many results in his four-volume treatise Theorie des Surfaces 1887-1896. Overview. It is intuitively quite familiar to say that the leaf of a plant, the surface of a glass, or the shape of a face are curved in certain ways, and that all of these shapes, even after ignoring any distinguishing markings, have certain geometric features which distinguish one from another. The differential geometry of surfaces is concerned with a mathematical understanding of such phenomena. The study of this field, which was initiated in its modern form in the 1700s, has led to the development of higher dimensional and abstract geometry, such as Riemannian geometry and general relativity. The essential mathematical object is that of a regular surface. Although conventions vary in their precise definition, these form a general class of subsets of three-dimensional Euclidean space R3, which capture part of the familiar notion of surface. By analyzing the class of curves which lie on such a surface, and the degree to which the surfaces force them to curve in R3, one can associate to each point of the surface two numbers, called the principal curvatures. Their average is called the mean curvature of the surface, and their product is called the Gaussian curvature. There are many classic examples of regular surfaces, including familiar examples such as planes, cylinders, and spheres, minimal surfaces, which are defined by the property that their mean curvature is zero at every point. The best known examples are catenoids and helicoids, although many more have been discovered. Minimal surfaces can also be defined by properties to do with surface area, with the consequence that they provide a mathematical model for the shape of soap films when stretched across a wire frame. Ruled surfaces, which are surfaces that have at least one straight line running through every point. Examples include the cylinder and the hyperboloid of one sheet. A surprising result of Carl Friedrich Gauss, known as the theorem egregium, showed that the Gaussian curvature of a surface, which by its definition has to do with how curves on the surface change directions in three-dimensional space, can actually be measured by the lengths of curves lying on the surfaces together with the angles made when two curves on the surface intersect. Terminologically, this says that the Gaussian curvature can be calculated from the first fundamental form, also called metric tensor of the surface. The second fundamental form, by contrast, is an object which encodes how lengths and angles of curves on the surface are distorted when the curves are pushed off of the surface. Despite measuring different aspects of length and angle, the first and second fundamental forms are not independent from one another, and they satisfy certain constraints called the Gauss-Kardashev equations. A major theorem, often called the fundamental theorem of the differential geometry of surfaces, asserts that whenever two objects satisfy the Gauss-Kardashev constraints, they will arise as the first and second fundamental forms of a regular surface. Using the first fundamental form, it is possible to define new objects on a regular surface. Geodesics are curves on the surface which satisfy a certain second-order ordinary differential equation which is specified by the first fundamental form. They are very directly connected to the study of lengths of curves. A geodesic of sufficiently short length will always be the curve of shortest length on the surface which connects its two endpoints. Thus, geodesics are fundamental to the optimization problem of determining the shortest path between two given points on a regular surface. One can also define parallel transport along any given curve, which gives a prescription for how to deform a tangent vector to the surface at one point of the curve to tangent vectors at all other points of the curve. The prescription is determined by a first-order ordinary differential equation which is specified by the first fundamental form. The above concepts are essentially all to do with multivariable calculus. The Gauss-Bonnet theorem is a more global result, which relates the Gaussian curvature of a surface together with its topological type. It asserts that the average value of the Gaussian curvature is completely determined by the Euler characteristic of the surface together with its surface area. The notion of Riemannian manifold and Riemann surface are two generalizations of the regular surfaces discussed above. In particular, essentially all of the theory of regular surfaces as discussed here has a generalization in the theory of Riemannian manifolds. This is not the case for Riemann surfaces, although every regular surface gives an example of a Riemann surface. Regular surfaces in Euclidean space. Definition and definition. Tangent vectors and normal vectors. First and second fundamental forms, the shape operator and the curvature, the curvature, the curvature, the curvature, the curvature, the curvature, 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 and the curvature, and the Christoffel symbols, Gauss-Kardashev equations, and the theorem egregium, isometries, covariant derivatives. Examples: surfaces of revolution, quadric surfaces, ruled surfaces, minimal surfaces. In 1760, Lagrange extended Euler's results on the calculus of variations involving integrals in one variable to two variables. He had in mind the following problem: given a closed curve in F3, find a surface having the curve as boundary with minimal area. Such a surface is called a minimal surface. In 1776, Jean-Baptiste Meusnier showed that the differential equation derived by Lagrange was equivalent to the vanishing of the mean curvature of the surface. A surface is minimal if and only if its mean curvature vanishes. Minimal surfaces have a simple interpretation in real life. They are the shape a soap film will assume if a wire frame shaped like the curve is dipped into a soap solution and then carefully lifted out. The question as to whether a minimal surface with given boundary exists is called Plato's problem, after the Belgian physicist Joseph Plato, who carried out experiments on soap films in the mid-19th century. In 1930, Jess Douglas and Tibor Rado gave an affirmative answer to Plato's problem. Douglas was awarded one of the first Fields Medals for this work in 1936. Many explicit examples of minimal surface are known explicitly, such as the catenoid, the helicoid, the Schurk surface, and the Inepper surface. There has been extensive research in this area, summarized in Osserman 2002. In particular, a result of Osserman shows that if a minimal surface is non-planar, then its image under the Gauss map is dense in S2. Surfaces of constant Gaussian curvature. If a surface has constant Gaussian curvature, it is called a surface of constant curvature. The unit sphere in E3 has constant Gaussian curvature +1. The Euclidean plane and the cylinder both have constant Gaussian curvature 0. The surfaces of revolution with pH/Tt equals pH have constant Gaussian curvature 1. Particular cases are obtained by taking pH/T equals C cos T, C sin T, and C et. The latter case is the classical pseudosphere generated by rotating attractrix around a central axis. In 1868, Eugenio Beltrami showed that the geometry of the pseudosphere was directly related to that of the hyperbolic plane, discovered independently by Lobachevsky 1830 and Ballier 1832. Already in 1840, F. Minding, a student of Gauss, had obtained trigonometric formulas for the pseudosphere identical to those for the hyperbolic plane. The intrinsic geometry of this surface is now better understood in terms of the Poincare metric on the upper half plane or the unit disk, and has been described by other models, such as the Klein model or the hyperboloid model, obtained by considering the two-sheeted hyperboloid Qx, y, z equals 1 in 3-dimensional Minkowski space, where Qx. Each of these surfaces of constant curvature has a transitive Lie group of symmetries. This group theoretic fact has far-reaching consequences, all the more remarkable because of the central role these special surfaces play in the geometry of surfaces, due to Poincare's uniformization theorem see below. Other examples of surfaces with Gaussian curvature 0 include cones, tangent developables, and more generally any developable surface. Local metric structure. Shape operator. Geodesic curves on a surface. Curves on a surface which minimize length between the endpoints are called geodesics. They are the shape that an elastic band stretched between the 2 points would take. Mathematically, they are described using ordinary differential equations and the calculus of variations. The differential geometry of surfaces revolves around the study of geodesics. It is still an open question whether every Riemannian metric on a 2-dimensional local chart arises from an embedding in 3-dimensional Euclidean space. The theory of geodesics has been used to show this is true in the important case when the components of the metric are analytic. Geodesics. Geodesic curvature. Orthogonal coordinates. Geodesic polar coordinates. Once a metric is given on a surface and a base point is fixed, there is a unique geodesic connecting the base point to each sufficiently nearby point. The direction of the geodesic at the base point and the distance uniquely determine the other endpoint. These two bits of data, a direction and a magnitude, thus determine a tangent vector at the base point. The map from tangent vectors to endpoints smoothly sweeps out a neighborhood of the base point and defines what is called the exponential map, defining a local coordinate chart at that base point. The neighborhood swept out has similar properties to balls in Euclidean space. namely any two points in it are joined by a unique geodesic. This property is called geodesic convexity, and the coordinates are called normal coordinates. The explicit calculation of normal coordinates can be accomplished by considering the differential equation satisfied by geodesics. The convexity properties are consequences of Gauss's lemma and its generalizations. Roughly speaking, this lemma states that geodesics starting at the base point must cut the spheres of fixed radius centered on the base point at right angles. Geodesic polar coordinates are obtained by combining the exponential map with polar coordinates on tangent vectors at the base point. The Gaussian curvature of the surface is then given by the second-order deviation of the metric at the point from the Euclidean metric. In particular, the Gaussian curvature is an invariant of the metric, Gauss's celebrated Theorema egregium. A convenient way to understand the curvature comes from an ordinary differential equation, first considered by Gauss and later generalized by Jacobi, arising from the change of normal coordinates about two different points. The Gauss-Jacobi equation provides another way of computing the Gaussian curvature. Geometrically, it explains what happens to geodesics from a fixed base point as the endpoint varies along a small curved segment through data recorded in the Jacobi field, a vector field along the geodesic. 1¼ centuries after Gauss and Jacobi, Marston Morse gave a more conceptual interpretation of the Jacobi field in terms of second derivatives of the energy function on the infinite-dimensional Hilbert manifold of paths. Exponential map. The theory of ordinary differential equations shows that if ft(v) is smooth, then the differential equation dv/dt equals ft(v) with initial condition v0 equals v0 has a unique solution for t sufficiently small, and the solution depends smoothly on t and v0. This implies that for sufficiently small tangent vectors v at a given point p equals x0 is 0, there is a geodesic CVT defined on 2 with CV0 equals x0 is 0 and CV0 equals v. Moreover, if s equals 1, then CSV equals CVST. The exponential map is defined by xv equals CV1 and gives a diffeomorphism between a disk VD and a neighborhood of P. More generally, the map sending PV to exp gives a local diffeomorphism onto a neighborhood of PP. The exponential map gives geodesic normal coordinates near P. Computation of normal coordinates. There is a standard technique, see for example Berger 2004, for computing the change of variables to normal coordinates u, v at a point as a formal Taylor series expansion. If the coordinates x, y at 0 are locally orthogonal, right, so v equals o plus lu, v plus lu, v plus, 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 uv equals bv plus mu, v plus mu, v plus, where L and M are quadratic and L and cubic homogeneous polynomials in u and v. If u and v are fixed, xt equals xtu tv, and it equals I2, tv can be considered as formal power series solutions of the Euler equations. This uniquely determines a b L. Gauss's lemma, Gauss's lemma. In these coordinates, the matrix Gx satisfies G0 equals I, and the lines TTV are geodesics through 0. Euler's equations imply the matrix equation GVV equals V, a key result, usually called the Gauss lemma. Geometrically, it states that, taking polar coordinates RTH, it follows that the metric has the form ds2 equals dr2 plus gr th dth2. In geodesic coordinates, it is easy to check that the geodesics through 0 minimize length. The topology on the Riemannian manifold is then given by a distance function dpq, namely the infimum of the lengths of piecewise smooth paths between p and q. This distance is realized locally by geodesics, so that in normal coordinates d0, v equals v. If the radius d is taken small enough, a slight sharpening of the Gauss lemma shows that the image U of the disk VD under the exponential map is geodesically convex, i.e. any 2 points in U are joined by a unique geodesic lying entirely inside U. Theorema egregium. Gauss's theorema egregium. The remarkable theorem shows that the Gaussian curvature of a surface can be computed solely in terms of the metric and is thus an intrinsic invariant of the surface, independent of any isometric embedding in F3 and unchanged under coordinate transformations. In particular, isometries of surfaces preserve Gaussian curvature. This theorem can expressed in terms of the power series expansion of the metric ds is given in normal coordinates uv as is uv as is v as is uv as is ds2 equals dotwo plus dv2 ku dvv dotwo slash 12 plus bv plus bv plus bv plus bv plus bv plus 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 Gauss-Jacobi equation. Taking a coordinate change from normal coordinates at P to normal coordinates at a nearby point Q yields the Sturm-Liouville equation satisfied by HRTH equals GR Thon/2, discovered by Gauss and later generalized by Jacobi. The Jacobian of this coordinate change at Q is equal to HR. This gives another way of establishing the intrinsic nature of Gaussian curvature. Because HRTH can be interpreted as the length of the line element in the TH direction, the Gauss-Jacobi equation shows that the Gaussian curvature measures the spreading of geodesics on a geometric surface as they move away from a point. Laplace-Beltrami operator. Gauss-Bonnet Theorem. On a sphere or a hyperboloid, the area of a geodesic triangle, i.e. a triangle all the sides of which are geodesics, is proportional to the difference of the sum of the interior angles and P. The constant of proportionality is just the Gaussian curvature, a constant for these surfaces. For the torus, the difference is zero, reflecting the fact that its Gaussian curvature is zero. These are standard results in spherical, hyperbolic, and high school trigonometry. See below. Gauss generalized these results to an arbitrary surface by showing that the integral of the Gaussian curvature over the interior of a geodesic triangle is also equal to this angle difference or excess. His formula showed that the Gaussian curvature could be calculated near a point as the limit of area over angle excess for geodesic triangles, shrinking to the point. Since any closed surface can be decomposed up into geodesic triangles, the formula could also be used to compute the integral of the curvature over the whole surface. As a special case of what is now called the Gauss-Bonnet Theorem, Gauss proved that this integral was remarkably always 2 times an integer, a topological invariant of the surface called the Euler characteristic. This invariant is easy to compute combinatorially in terms of the number of vertices, edges, and faces of the triangles in the decomposition, also called a triangulation. This interaction between analysis and topology was the forerunner of many later results in geometry, culminating in the Atiyah-Singer index theorem. In particular, properties of the curvature impose restrictions on the topology of the surface. Geodesic triangles. Gauss-Bonnet theorem. Curvature and embeddings. If the Gaussian curvature of a surface M is everywhere positive, then the Euler characteristic is positive, so M is homeomorphic and therefore diffeomorphic to S2. If in addition the surface is isometrically embedded in F3, the Gauss map provides an explicit diffeomorphism. As Hadamard observed, in this case the surface is convex. This criterion for convexity can be viewed as a 2-dimensional generalization of the well-known second derivative criterion for convexity of plane curves. Hilbert proved that every isometrically embedded closed surface must have a point of positive curvature. Thus, a closed Riemannian 2 manifold of non-positive curvature can never be embedded isometrically in F3. However, As Adriano Garcia showed using the Beltrami equation for quasi-conformal mappings, this is always possible for some conformally equivalent metric. Surfaces of constant curvature. The simply connected surfaces of constant curvature 0, +1, and 1 are the Euclidean plane, the unit sphere in F3, and the hyperbolic plane. Each of these has a transitive three-dimensional Lie group of orientation-preserving isometries G, which can be used to study their geometry. Each of the two non-compact surfaces can be identified with the quotient G/K, where K is a maximal compact subgroup of G. Here, K is isomorphic to S atwo. Any other closed Riemannian two-manifold M of constant Gaussian curvature, after scaling the metric by a constant factor if necessary. In the orientable case, the fundamental group G of M can be identified with a torsion-free uniform subgroup of G, and M can then be identified with the double coset space G/G/K in the case of the sphere and the Euclidean plane. The only possible examples are the sphere itself and tori obtained as quotients of R2 by discrete rank 2 subgroups. For closed surfaces of gen as G equals 2, the moduli space of Riemann surfaces obtained as G varies over all such subgroups, has real dimension 6×6. By Poincare's uniformization theorem, any orientable closed two-manifold is conformally equivalent to a surface of constant curvature 0, +1 or 1. In other words, by multiplying the metric by a positive scaling factor, the Gaussian curvature can be made to take exactly one of these values, the sign of the Euler characteristic of M. Euclidean geometry, spherical geometry, hyperbolic geometry, uniformization, Riemannian connection and parallel transport, covariant derivative. Connections on a surface can be defined from various equivalent but equally important points of view. The Riemannian connection, or Levi-Civita connection, is perhaps most easily understood in terms of lifting vector fields, considered as first-order differential operators acting on functions on the manifold, to differential operators on the tangent bundle or frame bundle. In the case of an embedded surface, the lift to an operator on vector fields, called the covariant derivative, is very simply described in terms of orthogonal projection. Indeed, a vector field on a surface embedded in R3 can be regarded as a function from the surface into R3. Another vector field acts as a differential operator component-wise. The resulting vector field will not be tangent to the surface, but this can be corrected taking its orthogonal projection onto the tangent space at each point of the surface. As Ricci and Levi-Civita realized at the turn of the 20th century, this process depends only on the metric and can be locally expressed in terms of the Christoffel symbols. Parallel transport. Connection 1 form. Global differential geometry of surfaces. Although the characterization of curvature involves only the local geometry of a surface, there are important global aspects such as the Gauss-Bonnet Theorem, the uniformization theorem, the von Mangold-Hadamard theorem, and the embeddability theorem. There are other important aspects of the global geometry of surfaces. These include injectivity radius, defined as the largest are such that 2 points at a distance less than R are joined by a unique geodesic. Wilhelm Klingenberg proved in 1959 that the injectivity radius of a closed surface is bounded below by the minimum of d equals p slash sub k and the length of its smallest closed geodesic. This improved a theorem of Bonnet, who showed in 1855 that the diameter of a closed surface of positive Gaussian curvature is always bounded above by d. In other words, a geodesic realizing the metric distance between 2 points cannot have length greater than d. Rigidity. In 1927, Cohn-Bosson proved that two ovaloids closed surfaces with positive Gaussian curvature that are isometric are necessarily congruent by an isometry of F3. Moreover, a closed embedded surface with positive Gaussian curvature and constant mean curvature is necessarily a sphere. Likewise, a closed embedded surface of constant Gaussian curvature must be a sphere. Liebman, 1899. Heinz-Hopf showed in 1950 that a closed embedded surface with constant mean curvature and genus 0, i.e. homeomorphic to a sphere, is necessarily a sphere. 5 years later, Alexandrov removed the topological assumption. In the 1980s, when constructed a story of constant mean curvature in Euclidean 3 space. Paratheory conjecture. This conjecture states that a closed convex 3 times differentiable surface admits at least 2 umbilic points. The first work on this conjecture was in 1924 by Hans Hamburger, who noted that it follows from the following stronger claim: the half-integer valued index of the principal curvature foliation of an isolated umbilic is at most 1. 0 Gaussian curvature. A complete surface in A3 with 0 Gaussian curvature must be a cylinder or a plane. Hilbert's theorem 1901. No complete surface with constant negative curvature can be immersed isometrically in A3. The Wilmore Conjecture. This conjecture states that the integral of the square of the mean curvature of a torus immersed in A3 should be bounded below by 2 π. It is known that the integral is Mobius invariant. It was solved in 2012 by Fernando Coda Marx and André Neves. Isoprometric inequalities. In 1939, Schmidt proved that the classical isoprometric inequality for curves in the Euclidean plane is also valid on the sphere or in the hyperbolic plane. Namely, he showed that among all closed curves bounding a domain of fixed area, the perimeter is minimized by when the curve is a circle for the metric. In one dimension higher, it is known that among all closed surfaces in A3 arising as the boundary of a bounded domain of unit volume, the surface area is minimized for a Euclidean ball. Systolic inequalities for curves on surfaces. Given a closed surface, its systole is defined to be the smallest length of any non-contractible closed curve on the surface. In 1949, Lohner proved a torus inequality for metrics on the torus, namely that the area of the torus over the square of its systole is bounded below by 3/2, with equality in the flat constant curvature case. A similar result is given by Pou's inequality for the real projective plane from 1952, with a lower bound of 2/p also attained in the constant curvature case. For the Klein bottle, Latter and Bavard later obtained a lower bound of 8/p. For a closed surface of genus G, Hebde and Borrego showed that the ratio is bounded below by 1/2. 3 years later, Mikhail Gromov found a lower bound given by a constant times gon/2, although this is not optimal. Asymptotically sharp upper and lower bounds given by constant times g/log g2 are due to Gromov and Bucer-Sarnak and can be found in Katz 2007. There is also a version for metrics on the sphere, taking for the systole the length of the smallest closed geodesic. Gromov conjecture a lower bound of 1/2, 3 in 1980. The best result so far is the lower bound of 1/8 obtained by Regina Rockman in 2006. Reading Guide. One of the most comprehensive introductory surveys of the subject, charting the historical development from before Gauss to modern times, is by Berger 2004. Accounts of the classical theory are given in Eisenhardt 2004, Kreyszig 1991, and Struick 1988. The more modern, copiously illustrated undergraduate textbooks by Gray, Abina, and Solomon 2006, Presley 2001, and Wilson 2008 might be found more accessible. An accessible account of the classical theory can be found in Hilbert and Cohn-Vossen 1952. More sophisticated graduate-level treatments using the Riemannian connection on a surface can be found in Singer and Thorpe 1967, Du Carmo 2016, and O'Neill 2006.